Okay, this is the last video for section 3.6. In it, we're going to try to classify our harmonic oscillators. So remember, harmonic oscillators were an example of something that would give us a second order linear, homogeneous, constant coefficient differential equation of this form. But unlike the generic one, where the coefficients in front of y double prime, y prime, and y could be positive, negative, or zero, with the exception that we couldn't have zero for the y double prime, here, m and k must be positive, and b must be non-negative. Okay. So, if we look at this, I can see that my characteristic equation is going to be ms squared plus bs plus k equals 0. And so my solutions, just using the quadratic formula, are going to be s is the opposite of b, plus or minus the square root of b squared minus 4mk all over 2m. So notice that's, I'll keep it going here, negative b over 2m plus or minus the square root of b squared minus 4mk all divided by 2m. Okay. All right, so there are basically four possibilities we need to look at. We could have b equals 0. That's the one coefficient here that's allowed to be 0. If so, we have an undamped harmonic oscillator. There's no damping force. Okay? And we saw that what that's going to correspond to is something that just goes back and forth forever and ever and ever, and the oscillations stay the same size. Okay? Now, if I look at what my solutions here are, if b is 0, this is 0, this would have to always be a purely imaginary number, okay? Because b is 0, m and k are positive, so I've got a negative under the radical sign. So we'd have just a pure imaginary pure imaginary roots, because I'd have to plus or minus two things. When we have that, we're going to have that the origin is a center. So if I were to look at the corresponding phase portrait for the corresponding system, the origin is a center. My solution curves just loop around, corresponding to y and v just oscillating between fixed values. Now the other three possibilities will involve b being 0, since it's not allowed to be negative, and we're just going to be taking a look at what this discriminant, the b squared minus 4mk, is. So I could have that b is bigger than 0, and b squared minus 4mk is negative. Now, of course, if I have that, that's going to mean that this is imaginary. Okay? So I'm going to have complex roots with a negative real part and a non-zero imaginary part. When we have that, we say that this thing is underdamped, and the origin would be a spiral sink. So my phase portrait would look something like so. So essentially, I've still got oscillations going on. It's just that the oscillations are getting smaller and smaller and smaller, and things are moving slower and slower and slower. Okay. I could have that b is positive, but b squared minus 4mk is bigger than 0. Now in that case, that's going to mean that this is real, so that I would have two real roots. Okay. Now, those two real roots would actually both be negative. Notice this is negative. I'm subtracting something with this root, but even if I'm adding something, the square root of b squared minus 4mk is going to be less than the absolute value of b, or less than b, because b is positive. So the negative part would be bigger than the positive part. So the origin would be a sink, and we say that a situation like this is overdamped. If I looked at the phase portrait, I would have my straight line solutions, approaching the origin. And I really wouldn't have any oscillations because my other solutions that weren't the straight line solutions would start out parallel to one straight line solution and then curve to come in tangent to another straight line solution. So there's really no oscillation going on at all. The damping force is too strong for that. The last possibility is that B is bigger than 0. And I'm sorry, what I wrote here, what I said was B is bigger than 0 and B squared minus 4mk is also bigger than 0. I'd initially forgotten to write the bigger than 0, so it looked like I was saying B was bigger than B squared minus 4mk. Sorry about that. All right, so I could have B is bigger than 0 and B squared minus 4mk is equal to 0. We say that a situation like this is critically damped. Okay. If we look at what this means for our roots, B is positive, so this thing is going to be negative, but this is 0. So that kills off this term. So this is the situation where I have just one root. So in the phase portrait, there would only be the one line corresponding to straight line solutions. And remember, this is the situation where it's like my solution curves want to be oscillating. They're trying to oscillate, but they can't because they get stopped by that straight line solution that they're not allowed to cross. So critically damped is sort of the boundary between stuff that does oscillate and stuff that doesn't oscillate at all. It's the stuff that tries to oscillate and just doesn't quite make it. Okay. So that's how we can classify our harmonic oscillators. Let's just take a look at one real quick example and see if we can't classify it. Let's suppose my mass was 5, my damping coefficient was 4, and my spring constant was 2. Okay. All right, so my characteristic equation would be 5s squared plus 4s plus 2 equals 0. The solutions would be s is equal to the opposite of 4 plus or minus the square root of 16 minus 4 times 5 times 2 all over 10. So that's negative 4 plus or minus the square root of negative 24 all divided by 10. So this is the case where our B was bigger than 0. It was damped. It was undamped is really simple. B is 0. Okay, this was damped. So the question is this underdamped, meaning that we do still get some oscillations, we would have a spiral sink? Is it overdamped, meaning we've got the two straight line solutions, which prevent there from being any oscillations at all? Or is it critically damped, meaning that we just have one straight line solution for our system, and it's trying to oscillate but just not quite making it? Okay. Well, let's take a look. If I look here, I've got the situation where I've got two complex eigenvalues with a negative real part. That's going to correspond to the phase portrait for the corresponding system being a spiral sink. Spiral sink corresponds to oscillations that are getting smaller and smaller and smaller, and so we would say this is underdamped. It's not damped enough to prevent oscillations from happening, but it's damped so that the oscillations don't just stay the same size. They're getting smaller and smaller and smaller as time increases. All right, that finishes up 3.6.